Hello physics students. Welcome to the second video in this very exciting topic of Newton's laws. So remember yesterday I mentioned that the goal of this unit is to link everything we've learned together, motion and forces, put them together through math to see how one causes the other. So today we're going to take a big step in that direction. We're really going to learn a law called Newton's second law that basically does that. It does it for us and finally brings everything together. Now, in the process, I usually, on a given year when we're in school, I spent about a whole period, 45 minutes, talking about the person who thought of this law, Isaac Newton, because he's an incredibly fascinating figure. And so, because we're now remote, we're doing this through a video, I have a feeling that the talk would not be as interesting if I talked for 45 minutes on a video. It wouldn't be as interesting as when we're in school and we're just taking a period and devoting it to like kind of story time. So what I'm going to do is really try and condense the history down and just talk a little bit briefly about it to put this into context. So one thing I didn't mention yesterday in talking about Galileo, a very important fact is that when he came up with his two parts of inertia, particularly that when objects in motion stay in motion unless you stop them, they don't require force to keep moving. And he applied that to the debate about the Earth going around the sun instead of the sun around the Earth. He actually suffered a lot. He was put under house arrest by the Catholic Church at the time. And so it's something that, we kind of forget about in the modern era, that the church was actually a governing body that had the authority to put people under arrest or even to execute them for things like heresy if you didn't agree with the doctrines. So this is the world that Galileo lived in. He came up with a very fascinating idea, but then he had to sort of back off and remain under house arrest. So the science always had to sort of pull back when it came against something and it limited the science. Isaac Newton completely changed that. Almost single-handedly, he brought us all into the modern era where science was free to reach conclusions and to really propel humanity. So again, I'm not going to go into too much of the biography, but I do want to point out that Isaac Newton did his work back in the 1700s, or was it late 1600s. So again, imagine the time. There's no electricity, there's no automobiles, there's no trains, there's no cell phones and computers, obviously. And it's just like the technology is like horse carriages and cannonballs, things like that, maybe bow and arrows, some primitive guns. So this is the state of technology. And then so you have this guy and he's basically at night just thinking, and his goal is to do what I've said, to make a mathematical model for the universe to explain why everything moves the way it does on Earth, out in outer space. So all he has is some books about geometry, things like that, philosophy, and a candle and a quill and some parchment, okay? So he's working, thinking at night, and with this tremendous, ambitious goal, and eventually he comes to the conclusion, writes 4 laws of motion. Well, 3 laws of motion: Newton's first law, second law, and third law, which we'll learn in this topic. And later in the year, something called Newton's law of universal gravitation. So you could say 4 ideas, 4 laws. He writes those down, and then he says, okay, now I want to explain everything mathematically, why forces create motion. But then he discovered that the math didn't even exist to take him to his final conclusion. So what did he do? He went ahead and invented the math. What do you suppose that math was? Well, some of you may know. Calculus. So someday, maybe now you're in calculus class, and you'll see how difficult it is. You'll have tutors and teachers and the internet and YouTube videos, Khan Academy, and you might still struggle with it. Now imagine someone who had none of that, and he invented it by a candle with a quill and parchment. Absolutely amazing. And then what he did is, once he had the 4 laws and that tremendous mathematical tool, he started to explain everything mathematically, including things like, why does the Earth orbit the sun in a circle, or actually an ellipse, okay? And with those 4 laws and calculus, he was able to prove all that mathematically and come up with an explanation. When he wrote his book, then he actually didn't suffer any persecution. It was so powerful that it stood on its own. In fact, what he did was so powerful that you, to this day, approximately 300 years later, you're going to spend the next few months of your life in physics class studying his ideas. So think about that, the power. And it's not just you. It's millions of people like you all across the country, all across the world, at high schools, at colleges, will spend months and months studying the ideas of Isaac Newton. Absolutely amazing. That's how powerful his ideas are. So again, I would have told a nice story about his what he was like as a kid, you know, what his mom described when he was born, all this stuff as a baby. But again, let's just jump right to that fascinating idea. Particularly today, we're going to look at Newton's second law, okay? So, what is this great idea that puts forces in motion? Well, we have some clues from the work of Galileo. Remember, objects stay at rest or in motion unless you act upon them. Another way to say that is they maintain a constant velocity, okay? So either 0 or 10 meters a second or 100, whatever it is, it stays that unless acted upon. What is that? How do you act on something? Force, right? You're pushing or you're pulling. So already we can say, flipping that around, so the force must change the velocity, right? If it's constant velocity without a force, then with a force, you're changing the velocity. And what's the word we use there? Well, what do forces do? Do they cause a displacement? No, you can be moving at a constant velocity with no force. Do they cause velocity forces? No, you could be moving with 0 force, or you could be not moving, or you could be moving faster. So forces don't directly create velocity either. The last thing in kinematics, linking forces to kinematics, not displacement, not velocity, it must be acceleration. That's the thing that Newton finally realized for humanity, for us, for you, for me, okay? That forces create acceleration. And not just that, he made a formula for that, okay? So let me step aside. Here it is. I'll give you a chance to jot this down. Okay, so here it is. This is his idea expressed as an equation. A is F net over m. Now, Isaac Newton, undisputed genius, okay? People will debate who's greater, Einstein or Newton. And you could go either way, you know? They'll go back and forth, and so brilliant. But this idea is incredibly simple. You've known it your whole life, okay? What do you know? Well, if you look at this formula, there are actually 2 ideas. Force is in the numerator of an equation that determines acceleration. What that means is if you put a bigger number here, you're going to get a bigger answer. Like, for example, 4 divided by 2 is 2. Let's do 10 divided by 2, 5. More force, more acceleration. Okay, so that's one idea. And you know this, okay? For example, if I take a marker, well, let's suppose this is a rock, and I say, I'm going to throw this at your head because you're being annoying. Ready? Right? It fell right. Everybody laughs. You don't duck because you see I'm not putting a big force on it. So you know, oh, geez, he's not putting a big force. It's not going to accelerate toward my head. But if you see me do this, yeah, right, and I throw it like this, now you're going to duck. You understand, oh, look, him putting that more force is going to accelerate more, it's going to go faster. You already know that, right? So simple idea. He just put it into an equation, which does a little bit more than more force, more acceleration. It tells the pattern. For example, if the force doubles, the acceleration doubles. Because there's no squared here or cubed or square root, we say that the force and acceleration are proportional to each other. Triple the force, you get triple the acceleration. So he went further. The second idea is how mass affects acceleration. Notice it's in the denominator. So if I have 10 force divided by 2 kilograms, I get 5 for acceleration. What if I have the same 10 up here, but instead of 2 down there, I put maybe like 8. So 10 over 8, a bigger mass, I get 1.25 instead of 5. More mass, less acceleration. And again, you don't need a formula. You don't need Newton for this, right? If I take a skateboard, empty, and I shove it as hard as I can, it's going to fly across the room. Now we take that skateboard and we stack a football lineman on it, 200-something pounds, right? And now when I push on that skateboard, same thing with all my might. You don't need Newton's second law to tell you that I'm going to go, and it's going to sort of creep along and accelerate at a lesser rate. You don't need the law. You know that already from common sense. So you know Newton's second law already, the ideas in it. But again, it goes further. It tells the exact mathematical pattern. If the mass doubles, double this over here, you're going to have a bigger denominator. The answer is going to get smaller by 2. Triple the mass, you're going to have a third of the acceleration. That's it, okay? Beautiful idea, simple. But here's the thing. Simple idea, and yet it's extremely difficult in a lot of problems to apply it. The application is difficult. You could spend your life learning how to apply Newton's laws and be stumped by something very simple, like something rolling down a ramp and hitting a bump and all, and it's very difficult right away. So let's take a look and start with some simple examples to try and understand how we can analyze things, situations with just math. So here's the first example. Let me go through it and I'll pause after. So we got a worker pushing a 20-kilogram box at rest on a frictionless surface with 100 newtons, and we're to determine the acceleration. This is the simplest problem we could do, but I just want to show you something that's important in Newton's laws, the ability to draw force diagrams. Since the forces acting on something are really what matters, we have to first catalog all the forces in a diagram to be able to begin thinking about what this net force means. So if I imagine this 20-kilogram box, one thing that's not even in the problem, but there's a force of gravity on it. Earth's pulling this down, so it would fall. But it's on a flat surface, so the flat surface supports with a normal force. We learned about that in the force unit. Now, where did I get this 196? That's this times 9.8. That's how hard the Earth pulls 20 kilograms down. 196 newtons. And then the worker pulls 100. So now, Newton's second law says the net force over the mass. Not the force, but the net force. So in this case, these two cancel. They add to 0. 196, 196, 0. They don't go in for a net force. The only force that's not canceled is this one. So that is the net force. 100 over 20 mass gives me an acceleration of 5. Okay? So let me pause and let you jot this down. Okay, so more force, more acceleration. We could see that in that equation. For example, if I were to say 200 force over 20 kilograms, then I get an acceleration of 10, right? So more force, more acceleration, right? Or if I say the same 100, but now the box, I dump some rocks into the box, so it's now 40 kilograms. Then I get 2.5 instead of 5, right? So those ideas are in there in this simple example. Well, let's move on to something just a little bit more challenging. Example 2. So we've got the same example as over here, but now we've got friction of 40 newtons. How does that change the calculation? Well, once again, what we have to do is always analyze by creating a force diagram. So always we do as simple as we can. We don't draw a worker or a box. We just draw the dot that represents the box, okay? All that's necessary. And we still have force of gravity. Oh, you know what? Maybe I'll move this over a little bit. Need a little bit more room. There's the box. We've got force of gravity. Again, 196, 20 times 9.8. We still have a normal force, same size, so I'll draw that arrow the same length, upward. And we still have the same worker pulling 100, so 100's like maybe like this. And then we have friction in the backwards direction 40, which is shorter than the 100, so I'm going to maybe do it like this. Okay, so there is my force diagram. So this one, I just had to add the friction. So again, I begin by writing out Newton's second law. Remember, same thing in the Regents where you always have to write out the formula. It's also the case with Newton's laws. And then what I'll do is think about these, the net force from the gravity and the normal force, 0. They're equal up and down. But this is not equal. So how do I find the net? Well, remember from the forces unit, I obviously have the 100 newtons. Well, maybe I'll color code it too. Why not? 100 newtons. And then I have the friction in the backwards direction. So I subtract that. 40 newtons. And that's all over the mass of 20 kilograms. So now I do 60 over 20 and I get an acceleration of 3 instead of 5 because the friction's holding it back a bit. It's still accelerating, still going faster, faster to the right. The speedometer, instead of going 0, 5, 10, 15, goes 0, 3, 6, 9, 12. It goes up by 3. So it's still speeding up, but at a lesser rate because of the friction reducing the net force a little bit. Less net force, less acceleration. So it's the net force, not the force, but the net force on an object. All right, we're going to keep going with examples. Let's see, maybe I'll be able to squeeze it in here without doing any erasing. So if you haven't already done so, go ahead and pause. I'll pause to go ahead so you could jot this down. Okay, let's go to example 3. I'll do this. V equals 10 meters per second. Okay, so here's the example. Draw a force diagram for the same box, gravity, normal force, same force of friction of 40 newtons, and you want to pull it at a constant velocity. This is a big theme in the Regents. for you to know that how to analyze something with constant velocity. What exactly does that mean? It comes up a lot in the Regents. So here's what you should be thinking, is the word constant velocity. What does that mean? Well, from the kinematics unit that we just finished, constant velocity is another way to say the velocity doesn't change, and if you have the same velocity of 10, 10, 10, 10, delta V over t is always 10 minus 10 over time, 0. That means this means acceleration is 0. Again, acceleration 0 doesn't mean you're stopped. It means you're not speeding up or slowing down or turning. So A is 0 from constant V. What does that mean from what we learned today? Well, if this is 0, for a certain mass, the only way that's possible is for the net force to be 0. So then we move on and say F net is 0. So that's the thinking that comes from the important words, constant velocity. Okay, so know that's what that means. So what that means now is the net force 0 means from the forces unit, all the forces have to balance. Whatever newtons you have one way, you have it matched in another direction. So the force diagram then now becomes, we've got force of gravity still down, still 196 newtons. The surface it's on still supports with 196 newtons. And that's what we call a normal force. The friction is still 40, so we draw something shorter than these two arrows. But the net force has to be 0. We must have a forward force to match that 40. A lot of people who don't understand physics well, who don't know Newton's laws, will look at a force diagram like that and say, oh, the thing's not moving, it's pulled equally in all directions, it's staying there. It's possible. That is a possibility, because that's also 0 acceleration. But you need to know, as a physics student who now knows Newton's laws and kinematics, the other possibility is that this is actually moving to the right at a steady pace. 10, 10, 10, 10, that's what the speedometer reads continuously. So in this particular case, this is not at rest. Not at rest, it moves to the right at a constant velocity, okay? All right, so if you haven't already done so, then I'll pause to give you a chance to jot this down. Okay, let's continue on with yet another example. Let's see, how do I want to... So here's the example. We got the same 20 kilogram box, but this time it's sliding on a frictionless surface at 10 meters per second, and we want to know the force required to decelerate it at 2 meters per second squared. Well, the A deceleration is an acceleration. It's just a slowing down acceleration. So the same law applies. A is F net over m. So to find the force necessary to produce that acceleration on 20 kilograms, what we do is we just start with Newton's second law. And this time, we knew the forces before and we were solving for acceleration. But now we know the acceleration. It's 2. And we're looking for the force net on 20 kilograms. So all we have to do is multiply the 20 to the other side, and we get F net must be 40 newtons. Okay, so there's the force net. Now, the force diagram. So here is the box sliding along, and again, this box is sliding like this, right? Sliding to the right with a velocity. Maybe I'll lower this a little bit because now I'm a little crunched up, so give me a little space here. Okay, so there's the box. We still have gravity and normal force. The Earth pulling down with 20 times 9.8 or 196 newtons. It would fall, but it's on the surface, and that surface is preventing it from falling by pushing up with a normal force of 196 newtons. That's why we have no acceleration in the up or down direction. F net is 0, stays horizontal. So now, which way do I push when this box is going to the right? Well, like this. There's that applied force of 40 newtons to slow this down. And that's it. A lot of students will make a mistake and they'll say, well, that can't be. What's keeping the box going forward? Because it's going to be going forward, and with an deceleration of 2, the speedometer will read 10, 8, 6, 4, 2, and 0. So for all these seconds, it's still moving forward and slowing down while I'm pushing it backwards. So it's kind of like this. This is the box right in front of me. Imagine it. And I'm pushing it backwards like this, but it's going like still in the forward direction, and I'm pushing it back. And so people say, well, what's keeping the box forward? And they put a force here, and then they say, because that's the box wanting to move forward. And then they say, I ask them, well, where did that force come from? And they scratch their head for a second. They say, oh, the box's inertia. That's the force of its inertia. And there is the mistake that Galileo corrected. Students still slip back into that idea saying that when something is moving, it needs a force to keep it moving. And no, it does not. Galileo said there is no force required to stay moving forever. So if I remove this, the box goes 10 meters per second, 10 meters per second, forward forever. I must put this to slow it down. And that's it. There's no forward force on the box, okay? So again, people will go back to the old way and forget about Galileo's work by putting a forward force. If you put a forward force, by the way, then the net force is 0 and the box goes at a constant, never slows down, okay? So that's the final example that I wanted to do today. But before I stop the video, there were a lot of ideas, and I want to write them down on one board to summarize all the examples that we've studied. So by the way, while I'm erasing here, if I haven't already done so, which I don't think I have, let me pause the video to give you a chance to jot this down. Okay, so I'll make a little bit more room because I may need a lot of room to summarize. Oops. Oops. So here's the big idea. Newton's second law links the force unit with the kinematics unit together right there, okay? And then we could look at for an object moving to the right, so if you have a force diagram that looks like this, where you have gravity down, normal force up. You know what? I'm going to run out of room. I got to draw it a little smaller. If normal, forward force, and then some kind of backwards force that's shorter. If the object's moving to the right, and that's the force diagram, then what happens is it continues to move to the right, and it speeds up, okay? By the way, I didn't mention this, I should have, with all the force diagrams that I did, that you don't need to put that this is 196 newtons and 196 newtons there. You don't have to, when you're drawing a force diagram on the Regents or on a physics test. What you need to do is just have a down arrow and label it properly as FG and FN, FF, F. The values do not need to be on a force diagram when you're drawing it for credit on a test. Later in the problem, you might need the values. Okay, so that's one example when something speeds up. The second example we did was the same box, same force of gravity, looks about the same. That means the same normal force of the surface underneath supporting it. Pulling it forward with, say, 100 newtons. And then the backwards force is an equal 100 or whatever it is, but the same amount of newtons in the backwards direction. So these are equal, which we could go like this, right? That says they're equal. And a lot of students will say, who don't understand Newton's law, oh, it's at rest. Maybe it is. But the other thing is if it was already moving to the right, it'll be moving at a constant velocity. Of course, we could fill that out more with words. Neither speeding up nor slowing down, steady. Okay? And the last example we looked at is something, of course, same gravity, the same normal force, and then we've got no forward force, but we've got a backwards force. Oops, uh-oh, mistake. Force of friction. Of friction, or maybe that's you pushing backwards, that you know this doesn't mean it's moving to the left. If it's moving to the right and you have this, there's no forward force. This is something moving right and slowing down. You need a net force in the backwards direction to slow down. All right, so let me pause the video, give you a chance to jot this down. Okay, so there it is. Our first big, huge step in putting everything together. How do forces create motion? Through this equation. More force, more acceleration, more mass, less acceleration, puts everything together. So from now, what we have to do for the rest of the unit is we have to learn Newton's third law. Very fascinating also. That's coming in another video. And then for a long time, if you look in the schedule, what we're going to be doing is applying these three laws to just a bunch of situations. A car going down the road, something sliding down a hill, rockets and elevators moving. So we're just going to be applying in the same manner. Force diagram, equation, solve. Okay? So that's it for today. I hope you enjoyed the video. I'll see you in the next physics video.